Okay, I guess we'll get going because it's 4:30. I do have announcements. Yay! Because it's after reading break and tons of stuff has happened. Nothing has happened. Other than, yeah, the room is different. So I'll try my best. This is definitely a reduction in space, but I wasn't using all the space anyway, so I guess I could just do this. Now I have two boards. Kind of. So normally I would say what we did last week, but that was before the reading break, and we're switching to a new topic anyway. So it was trees. We finished up our discussion about trees, binary search trees, ways to search through trees, that sort of stuff. So nothing really to say there. Every grade should be posted now for the quizzes and the assignments and all the stuff that I had sitting there. If it's not, let me know because I have it all, like I grade it all in front of me and then I post it. So if something's missing, just be like, Travis, you missed this. And I'll be like, okay, sorry. Because it's just how it is sometimes. Just forget stuff. When there's because I have two sections now, so 80 students. When there was two quizzes, I might have just missed one. So please check, make sure I put the grade there. If not, just send me an email. I want to say that assignment 2 is due, I think it's October 26th. I am going to change that to October 27th because I haven't posted it yet. I'm going to do that tonight, and I feel a little bad saying you have 5 days to do it. So actually, you know what? Screw it. October 28th. Because now it's 7 days. I don't like giving less than 7 days for an assignment. I think that's not fair. I'm just making some final tweaks on what I want to ask about graph theory because that's the hard part. Just figuring out a good question to ask. But again, these chapter review assignments are still kind of short. It's basically like 3 quizzes in one, so they're not meant to be super long, right? So a week is more than enough time to do it. The first group project, I think, is due 2 or 3 weeks from now, so I'm also finalizing that to post. So group project 1 due November ? I don't have it in front of me. It's in the course outline. It's I think it's I think it's 2 weeks from now, on the Saturday or something. Anyway, that will also be posted. This is the one where you have your groups that you submitted.
November 2nd.
Thank you. Now that you've told me that, I can say that was my guess, and I can't prove or disprove it. But yeah, that'll be due on November 2nd. That'll be posted. If not tonight, then tomorrow. Because like I said, I'm just finalizing it. I'm trying to think of an interesting programming question that is accessible halfway through the term. Because like the end stuff is like, well, then you've done the whole Python course, so that one's pretty easy to figure out what to do. But at this point, you're still kind of like in the middle of it, so it's hard for me to. It's probably just going to be do some recursion stuff, right? So it'll just be implement some recursive algorithms, which isn't too bad. So anyway, I'll post that. But I think that's all I have. So I think we're just going to jump straight into it, which is it's funny that we have like 4 chapters in this, and they're all kind of very distinct. So it feels like we jump around because we do. This one though. We are going to take a mathematical approach to this, but I think for people in programming, it should be obvious why you would care about working in other bases, such as binary and hexadecimal. In your web development, at this point, you've already seen, like working in CSS or even in HTML when you're using color codes, it's six characters in hexadecimal, right? So it has value, knowing this stuff, but we're going to take a mathematical approach because there's nothing special about base 10 or base 16 or base 2. They all have interchangeable concepts that we can talk about. So we might as well talk about them in a broad sense. So one thing to note, starting this off, is it's a bit weird because we're very, 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 very used to working in base 10. So the concept that numbers, the number, and the symbols we use to represent them being different seems weird at first. So numbers and their symbols I guess I could say don't need to match base 10. So the normal system of writing that we're used to. And there's some really easy examples, even without delving into different bases, on how we can represent the same number different ways. So that my goal is to say that's not even that weird. So ways to represent 14 as a number. So of course 1, 4, right? This is base 10 Arabic numerals. So this is the way of writing numbers that we're very, very used to. But that's also 1, right? That also means 14, Roman numerals. And, you know, if you have at least some baseline experience with Roman numerals, you would look at these and you'd be like, I understand these are the same thing. Very different symbols to represent the same number, but they represent the same number. Another one, ticks or tallies, right? You're a prisoner counting the days. This is another way to represent the number 14, right? So these all represent the number 14. So because of this, we have different symbols to represent that number. So then, you know, nobody's going to ask questions about these symbols, right? You know, okay, yeah, so this is a different way. But then that means a natural question is, does 14 have to be those symbols? Like, why are they those symbols, right? At some point, we just decided those were the symbols. So, yeah, of course, that's what we're used to, but does it have to be these symbols, right? So, another example that sort of leads into this conversation is, imagine in your head 512 loonies, right? Just a pile of 512 units. Is that a good way to represent $512? No, that's a terrible way to represent $512, right? How would you represent it? 5 $100 bills, 1 $10 bill, and a toonie, probably, right? Or 2 loonies if we want to talk in the language of base 10. So that kind of means this way we probably don't want to gravitate towards also. That's not a generally good way to represent it. But that's sort of motivation, right? And we're talking about the concept of $512. We don't represent it as 512 loonies, even though that is conceptually what that amount of money is. We represent it as, you know, 5 100s, 1 10, and 2 1s. So we can think about what we call base 10 principles. So there's kind of 2 rules for base 10, really. So if we think about it, each position, so like we've got, here, I'll write down the example I gave. So this is 100s, 10s, 1s, right? This is like going back to grade school thinking about it in these terms, right? But this is the 100s position, the 10s position, the 1s position. So each position on the left is worth 10 times more than the previous one, right? Each position moving left is worth 10 times as much as the previous. And another condition, if we ever end up with 10 in one of these positions, we exchange it for 1 to the left. So think about it this way. You have 10 $10 bills. You can go to the bank and say, give me a $100 bill, right? You can exchange 10 $10 bills for a $100 bill. So all digits must be less than 10. And so I'm writing the word 10 here because we're sort of having a conversation about the idea of numbers being different than the symbols representing them. So if I wrote down this, then is that 10? Not necessarily, right? Because if we're talking about binary, then that is not 10, right? So we need to be very careful, right? That would be 2 in binary. So I'm using the words here to indicate the actual numbers. These represent the symbols. So that means if we needed 10 objects in one position, exchange them for 1 to the left, or I'll say 1 to the left. So the symbol, so valid digits, in terms of symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We do not have a digit representing 10 in base 10, because if we got there, we would just trade it for 1 to the left. Now the point here is, I have them in my pocket, which is a terrible place to put markers. But I'm calling this base 10 principles, right? There's nothing special about 10. So if I just cross that out and instead say 2, oh, there's one more here. What are base 2 principles? Well, each position moving left is worth 2 times as much as the previous. So this would be the 1's position, the 2's position, the 4's position, the 8's position, the 16's position, and so on, right? All digits must be less than 2. If we needed 2 objects in one position, exchange them for 1 to the left. So in this case, we now lose all of these digits in base 2, right? It's just 0 and 1. And that's binary, right? We call this base 2, but this would be binary, right? That we maybe know and love in computing. But there's also a possibility here. I almost went to go grab a marker. They're in my pocket. This is going to take some getting used to. Oh, goodness. So another, again, common example in computing is 16. Right? So we, again, just write 16 instead. And everything still works. There's nothing special about the number we choose here. Other than once you start getting really big, we're starting to question why we're representing numbers that way. So like you could talk about base 42 if you wanted to. And it's like, okay, but like now I have to invent 42 different symbols to represent my digits, and it's getting a bit much. But this is a very common one. This is hexadecimal. And the reason why it's useful in computing is 1 hexadecimal digit represents 1 byte. So 2 bytes, 2 bytes. No, it's 1.
No, it's half of a byte.
Yeah, it's half of a byte. Yeah. 2 symbols represents 1 byte. Yes, thank you. So these are useful in computing, right? So if you ever you can open a piece of software or any file on your computer actually in a hex editor, and that's just really useful for examining files and figuring out memory pointers and that sort of thing, because everything in terms of memory is usually done in hexadecimal. Memory addresses are written in hexadecimal, so if you ever get an exception, it'll probably tell you which memory address it lives in. But now we have this question here. Valid digits. Okay, well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now, okay, we're out of classical digits. I mean, again, you've seen this in HTML, so this isn't a surprise. But we just start adding letters now. A, B, C, D, E, and F. Right, so this, A, represents 10. Right, so this is really, really important. And this is something that really trips people up when they're first working with bases higher than base 10, is we have to write A because your natural instinct is to write that, 1, 0, right? That's not a digit, that's 2 digits, right? 1 and 0, we've already declared, 2 separate digits. So this represents a totally different number than A, right? This would represent 16 in base 16, right? So you have to be careful. A digit is a single symbol, right? So one of these for hexadecimal, one of these for base 10, and 0 and 1 for binary. Or true and false if you want for binary. Okay, so these are the principles. So really we could think about these different bases as essentially the language of numbers, right? These are all different ways of communicating the same concept, which is essentially a language, right? Think like, this. Does anyone know a language other than English? Because this is a TV, television. Does anyone know what that word is in some other language? Sure. There we go. There's multiple, right? So we have multiple ways of referring to this exact same object, right? And they're different languages. Same thing here. We have multiple ways of referring to the same object, but notice what I kind of just did there. I was like, hey, what's this? And we all called it the same thing, which means we can translate between languages, right? That's something that we can do. So that's what we want to examine. Is if we're going to claim that this is sort of the language of numbers, I don't know if I would say the language of mathematics, but at least the language of number systems, we need to be able to translate between languages. Otherwise, we can't communicate, right? So, imagine, like, why did we choose base 10? It's pretty obvious. I have 10 fingers, right? So we just operated in base 10 because when we were thinking about numbers in the first place and representing the idea of counting, we used our fingers probably. So you can imagine a situation of like some sci-fi alien species that has 12 fingers. They probably very easily count in base 12. They probably have completely different symbols, but there's 12 of them, right? And that's how they represent numbers, right? So let's just start with an example here. Let's convert the base 8 number (512) in base 8 to base 10. So this is a pretty natural question, right? I've been presented with a brand new language, and I'm like, well, I speak English. So I want to figure out how to translate that language to my language. And that's what we're doing here, right? We speak in base 10 most of the time. So how can we convert from this to this? Actually, one quick note here about the notation. It's another one of those things. I'll drive it home, and in a room of 80 people, someone will make the mistake. This is a subscript for base. It is not part of the number. It is not 5128. It is 512 base 8. It's a little harder to see it on the board, but especially in text, it's very much smaller and lower. It is a subscript. So keep that in mind. Don't mistake this as the number 5128 in base 8. It will lead to problems. Okay, so we essentially want to lean on this concept, right? These are called place values, and we can build what's called, this is essentially a place value chart, right? Each of these digits represents a certain numerical amount. right? So we can just figure out what that numerical amount is. So we build a place value chart. So what does that look like? Well, I like to build it as sort of a table. So we have these digits in it, right? 5, 1, 2. And we have these place values. So if we were talking about base 10, this would be the 1s, the 10s, and the 100s, right? But that's not what we're dealing with, right? We're not dealing with base 10, we're dealing with base 8. But we still use the same exact idea here, right? Right here, each position moving to the left is worth 10 times as much as the previous. In our case, we're in base 8, so it's 8 times as much as the previous. So this right here is always going to be the 1s position. This next position is worth 8 times as much, so this is 8. This is worth 8 times as much. So 8 times 8 is 64. Right? So this is the 1s position, the 8s position, and the 64s position. It's more common to write place value charts as powers of our base. So in this case, this would be 8 to the 0 is 1, 8 to the 1, 8 to the power 2. Right? Because if we start here, 8 to the 0, multiply by 8, we just increase the exponent by 1. Multiply by 8 again, increase the exponent by 1, and so on. Right? So we just do that. But now this is kind of telling us what we need to do, right? In this example, I said this is 5 $100 bills, one $10 bill, and two $1 bills. We have coins in Canada, but bills, right? So this is a $64 bill, an $8 bill, and a $1 bill. Imagine you live in a country where that's the denominations of currency they use. So this is 5 $64 bills, right? And I'm even going to use the number, like money, to drive the point home, right? This is 5 $64 bills. This is one $8 bill and two $1 bills, right? Because if that's the denomination of my currency, if I just, do this, count this up, that's how much money I have, right? And that's essentially what we're doing here, right? We're just saying, take my weird denominations of currency and figure out how much money I have, right? So this is, I can't do that in my head. 8 plus 2. So this is saying if you have 5 $64 bills, you have $320 plus another $8 plus another $2. So that is $330. So if I use this weird currency denomination, that's how much money I would have. So in the end, we would say 512 in base 8 is 330 in base 10. Now, one thing we often do is we omit the base 10 because that's the one that's to be understood that we're working in, generally speaking. So it would be okay if you wrote it like this and just said 330, right? So I would say I read this number out as 512 in base 8 because saying 512 in base 8 is maybe a bit misleading, because is that the digits 512 in base 8, or is it the number 512 being represented in base 8, which are two different things? But here there's no confusion, right? 330, the number matches the digits, right? That's just what it is. So I'm not going to call anyone out on that. Like if you said, Travis, that's 512 in base 8, I'm going to be like, no, it's 512 in base 8. Like, no, it doesn't matter that much. But that's how I will talk, right? Because I want to make sure the distinction is clear. These are symbols used to represent digits. This right here, the digits match the number. Okay, so let's just do another example. But let's work in, say, base 12. I might need some calculator help because I'm once again deviating from my notes, which is something you should never do. But I like to live dangerously. So let's convert the base 12 number. Let's do A1 7 to base 10. Okay, so we do the same thing, right? We build this place value chart. So we've got A, 1, 7. Now this is already kind of weird because we're not used to using letters for numbers in terms of counting. Again, you've seen hexadecimal with hexadecimal codes for color codes, but at that point you probably just look at it and you're like, yeah, that's just a thing I do in CSS, right, for colors. But there is something more going on here. These symbols mean something. And the top here is exactly the same. So we start at 1, which is 12 to the power 0. We go up by 12, 12 times bigger, or 12 to the 1, and we do the same thing. We get 12 times bigger, and so this is 144. 12 to the power 2. So same exact thing. We ask, okay, these are weird denominations of bills, and these are how many bills I have. So we have, and when we write it down like this is where it's a bit silly. We have A $144 bills, and we have 1 $12 bill, and 7 $1 bills. Okay, so that's reading exactly what we see here, but now we're talking about converting to base 10. So we no longer have to worry about like representing this, right? We can now actually start writing numbers in base 10. Everything here is going to be in base 10 now. So write in base 10. So what is A? Well, it's the next digit after 9, so it's 10, right? So this digit here means 10. Close enough. So at base 10, we would write that as actually just 10, right? Times, so we have 10 $144 bills, and we don't really need to do much else. So this is 1,440 plus 12 plus 7 is 1459, if I didn't screw that up. So if I used this weird denomination of currency, and I had these symbols to represent the amount of bills I had, then I would say, I have $1,459 in this currency, right? So we kind of see here that converting from another base to base 10 is actually pretty straightforward, right? If it helps you, especially when you're early on, think of that money analogy, right? Like these are bills in a denomination, right? So 100s, 10s, 1s, except they're different from that. And this is how many of those bills I have. So if you have that in your head, you can ask yourself, how would I count this money, right? And then the answer becomes clear, right? You just write down how much you have of each. But if we're talking about a different language and translating it, well, it's not very useful if we can only go one way, right? So natural question is, okay, we can convert from a base to base 10. So now let's go from base 10 to another base, right? Because naturally, a very common base conversion is going from binary to hexadecimal or vice versa, right? It skips base 10, right? We don't have base 10, so it goes from binary to hexadecimal. So that's our goal, right? Is to basically translate from one to another. So let's convert. I'll write an example. So let's convert the base 10 number. I'm going to start with the example I have into base 5. Okay, so we're essentially going in reverse, right? So how can we do this? Well, we still want to build a place value chart, right? So the base 5 representation of this number is essentially what goes in this table, right? So let's start with that. Let's start with building a table. And the difference here is we don't know how big the table needs to be, right? So we're just going to go ahead and build it. So we've got our ones position, which is 5 to the 0. And then we go 1 over, which is 5 to the 1. 1 over, which is 5 to the 2. It's our 25s position. And then we've got 5 to the 3, which is our 125s position. And then we've got the 525. 5 to the 4. So now I can kind of see here, I don't need to go any further, right? Because if I were to represent the number 324, like let's say the goal here is giving change essentially, right? I want $324. What bills do I give you in this denomination? Well, I wouldn't give you any $525 bills, right? Because that's bigger than the amount of money you asked for. In this case, all right, we know we don't need to go any further, right? You just essentially keep listing them until your number gets bigger than, your denomination gets bigger than whatever number you're representing, right? So, okay, but now, that's a good analogy to think of, is I have $324, I would like however many bills in this denomination, right, for making change. So,
5 to the 4 is 625.
Thank you. Don't do mental math in front of people. I think that's even written down in my notes. It is. I could have just looked. But now the question is, what do we put here? Right? And it's pretty easy to sort of just guess in this case because the numbers are small. But we want to sort of come up with something a bit more algorithmic, right? Something that we can just do no matter what numbers are involved and what denominations are involved. The same process will work every time. So we have to ask ourselves, how many $125 bills go into 324, right? So a couple ways to think of that. I think the most natural way that students end up doing is they just say, okay, I have 324, and I just take away 125 until they can't anymore, right? Until it goes negative. But personally, the way I think about it is divide this by 125. This isn't in my notes. Does anyone have their calculator open? This is going to be like 2 point something, right? And I just want to know what the point something is. Ish.
2.592.
592. Okay. So this is the natural way to do it. So what this is telling us is this is sort of how the division algorithm works. This is there are two groups of 125. Two groups of 125 fit into 324 with some stuff left over. For the purposes of our algorithm, we don't really care what that is because the point is we want this part, right? The 2 point something. That's all we care about. Yep.
Since we're looking for whole numbers, could we not just use a modulo?
Yes, we could. So this is, I'm going to get to that. So this is pretty easy to implement as an algorithm using modulo instead, because what we want is essentially we can, in Python, we could just do this instead, right? The double slash, which is integer division. So that would give us the 2, and then we can get the remainder with modulo. Because what I'm about to do is I'm going to ask, okay, so we want 324 minus the 2 copies of 125. That's how much change is left to be given, which is 74. So now I have $74 left to do, but this is a 2. Right? This is integer division. That's the remainder. Right? So now we just continue. Right? Now I know how many $2 bills I have. So then 74 minus how many $25 bills do we have to give? 2. Right? At this point, you don't even need to really think about it. This is, 5 times 25. That's going to give 24. But the point is, this is a 2. And then we rinse and repeat, right? 24 minus 4 groups of 5, which is 4. And then the last one, well, how many ones do we need? I'll write it down, but just for the purposes of, hey, this is an algorithm. We got to 0, so we're done. Right, so it really is like a making change process in terms of using the least number of bills possible. So what we now know is that 324 is 2, well, technically you could write it as 0, 2, 2, 4, 4 in base 5, but I mean, technically we would write that as 0, 3, 2, 4, so we tend not to write leading zeros, right? They don't add any information. Okay, so this is the general concept for converting from base 10 to another base. So let's just do one more example, except we're going to do it together, essentially, because I'm going to ask for random numbers, which, again, can be a disaster. But so let's convert the base 10 Give me a base 10 number. Be reasonable.
72.
Sure, why not? To base. Give me a base.
11.5.
That's not a base. They have to be integers. 6. Sure. All right, so we're going to convert the base 10 number 72 to base 6. So we follow this exact same process. And, oftentimes when I'm like, hey, give me some random numbers, the point is to show you that nothing here matters. None of these numbers matter. The process works the same no matter what you pick, right? It's the same thing when I was like, okay, let's do a GCD. Give me random numbers, right? And we just did it. So this is the same thing. So what we want to do is we want to build a place value chart. And how big does it need to be? I don't know. Let's find out. So we always start with a 6 to the 0, which is our ones position. And then we have a 6 position. Then we have a 36 position. And then we can go 1 over, but spoilers, it's not going to matter. So 6 cubed is 326.
No, it's 216. 216.
That's close. Ish. But this is the idea, right? So at this point, we're trying to convert the number 72 to this base. This is way bigger than 72. So we're going to have a 0 here, right? So you can write this as part of your place value chart, or you could just know that, this fits in here less than 6 times, so we don't need to go any further, right? But now, same thing. We say, okay, 72 minus how many times does 36 fit into 72? Oh. Well, that can happen sometimes, I guess. That's really funny. So anyway, nothing left over. So that's 2, 0, 0. So I'm sorry, I'm going to have to take away the 72. I know. Well, you wrote the answer down, but I'm just going to do one for those who are, I don't know, for myself. This is for me. Let's do 319. Why not? Okay, so now this 216 matters. So this fits in once. 319 minus 1 group of 216. This is 103. And now we rinse and repeat, right? So we just ask ourselves, okay, with what's left over, how many 36s do I have? 36, 72, that's it. So 36. Yeah, so it would be 108. So this is going to be 31. So 2 fit in. Again, just sort of rinse. This is the point, right? It's like an algorithm, right? We just sort of go through the motions now. So from 31, How many $6 bills do we need to give? 6, 12, 18, 24, 30. So 5. Oops. And there's 1 left over. Right? And then from 1, how many $1 bills do I give? 1. And we're done. So that means 319 is 1251 in base 6. And, you know, if you didn't want to write this down, 72 in base 6 was 200 from the previous one. So one thing to note here is as your base gets smaller, and this kind of makes sense just, you know, if you know binary, as your base gets smaller, the number of digits or places you need to not digits, the number of places you need to represent your number grows larger, right? Because you can essentially represent less stuff in each spot. So in base 6, we only have 6 choices here. In base 10, we have 10 choices. In base 16, we have 16 choices. So we could sort of capture more information the more symbols we have. And the less symbols we have, the less information we can capture, right? Okay, so let's do another example here. But the example that's sort of like computer-y, to say the least. So let's convert 10100011 to hexadecimal. So this is something that computers would do, right? Go from binary to hexadecimal. I mean, they would do it very directly because it's really easy to actually go from binary to hexadecimal specifically. And if you end up working in specific types of things like hardware, you'll probably be able to just do it in your head. But for now, let's just say we're not worried about how computers do this, right? This is just what we're doing. So this is how we would write this. Is we would say this is in base 2, right? And the language we're using, this would be base 16. Okay, we want to convert this to base 16. So a natural thing to ask is, how can we do that? Well, if we think about it, we're in base 2 here. And our goal is to get to base 16. Well, let's think about this in terms of languages, right? So I speak English natively. I did learn French in university, but let's say then I started learning Japanese. And I wanted to translate French to Japanese. How am I probably going to do that? Unless I am extremely fluent in both of those other languages, I'm gonna add a middleman, right? I'm gonna go from English or from French to English, and then from English to Japanese, right? That's sort of the easiest way to do it. For arbitrary bases, again, for specifically binary to hexadecimal, there's like a sort of easy way to do it. But for just 2 random bases, this is how I would tackle it, right? Again, if I wanted to go from French to Japanese, I would go French to English, and then English to Japanese. With the difference of with base conversions, there's no loss here. Like if you go from one language to English to another language, you probably screwed everything up, right? You've lost information because some idiomatic expression in French doesn't even have an English equivalent, and now how do you translate the Japanese? You can't. But let's use this as our motivation, right? So we're gonna go from base 2 first to base 10, which means we have to draw our big, nice place value chart, which hopefully I have enough space here. So this is 1. I'm just gonna write down the positions 4, 8, 16, 32, 64, 128, and that's all I need. So these are all powers of 2, right? 2 to the 0, 1, 2, 3, 4, 5, 6, 7. And we have our binary representation here. And so now we just go through the motions, right? It's really nice with binary because either it's 1 times this number or you don't write it down, right? So it's 1 times 128 plus 1 times 32 plus 1 times 2 plus 1 times 1. Boom. Easy. But I'm not going to do that in my head because I'm lazy. So it is 163. Cool. All right, so that's step 1 done, right? We went from base 2 to base 10. So now we just have to go from base 10 to base 16. And we also know how to do that. Okay. Now we just build our place value chart. So we're dealing with base 16. So this is our 1's position. And then we've got our 16's position. And then we have our 256's position. And, well, that's already bigger, right? So we don't even need to, this is a 0. So we ask ourselves, how many groups of 16 fit in here? So it turns out it's 10, right? 160. And so we have 3 left over. And this is the thing that when you start doing this, people screw up pretty quickly. Is that right?
No.
Yeah, right? No, because this is 2 digits. So remember in hexadecimal, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A is 10. So we have to write down an A. And then we say, okay, well, 3, how many groups of 1 fit in here? Just 1. So that means 1, 0, 1, 0, 0, 0, 1, 1 in base 2 is A3 in base 16. Now this example here is not just completely random. This is if you are familiar with Unicode tables, this is what you would see here. So this, I have to look at my notes because I don't remember specifically the symbol. This is, which is the British pound symbol. I don't even know how to write that like that, I think. So this is a type of conversion that your computer does like constantly, right? It doesn't do it this way. It doesn't go to base 10. It just does it directly because everything is in base 2 in a computer. So it going to hexadecimal to do a lookup in a table is very straightforward. And again, underlying, it's still all binary at the end anyway. But we represent the Unicode table as hexadecimal. And this is how, there's an encoding method here. There's some extra stuff that goes on to encode something as Unicode to indicate that this is the symbol that you are going to get. But my point here is that this exact conversion is something that comes up all the time, right? If you were looking at non-ASCII characters, then your computer does this exact type of conversion with a bit of extra stuff for encoding reasons. So, you know, it goes back to that thing of me saying, hey, if I'm teaching you something, I better be able to say this is where it appears, right? This isn't just me saying, hey, we're doing base conversions because they're fun. I think they're fun. I think lots of math is fun, but this is the reason. But let's go back to a comment that was made. There is sort of a programmatic way to implement this, right? So right here, I'm saying, okay, we need to find essentially 2 numbers to continue to the next step. This is what goes in my table, right? Well, I have to convert it to, you know, the hexadecimal value. It's not 10, it's 8, but that's easy enough with a dictionary. And then there's this symbol right here, the remainder that I need, right? So I need the result of integer division, and I need the remainder. Well, there's 2 exact operations in Python for that. So programming-wise, we can simplify this to 163 integer division by 16 gives 10. and then we put that in the table, and then 163 modulo 16 gives 3, right? So this is sort of our one step. So we're going to take this, and then we put it into our table. So this would be A, right? After we do, I'll look up in a dictionary to figure out which symbol corresponds to that number. And then we just repeat again. So now our remainder goes here, and then we just move along the place value. Right? This is what we write down. This is 0, so we terminate. And we're done, right? So we just need to know these place values at what step we're at to put here. We need to know what we started with, and then we just carry this forward, right? So you can do this iteratively. So, shocker, there will be a homework assignment where you implement a base converter. And it's not complicated, right? You just need to, have you talked about dictionaries?
Yeah.
Yeah, okay. So my advice, this is easier to do with a dictionary, or easiest to do. There's lots of ways to do it, but I would store, I think the way I have the question phrased is convert from any base that the user specifies between 2 and 16 to any other base that the user specifies. So, you know, you have to have a hash table, so a dictionary of these digits, and that's it, right? And then just when this operation spits out 10, you look in your you don't even need a dictionary. You can do this as an array too. 10 would correspond to 8, right? Boom, done, right? So anyway, that's for later. Okay, what time is it? I think I will torment you with your own example before I move on. These are things you'll do one, and then you'll be like, okay, I get it, right? If you haven't already, then once you actually do one yourself, you'll be like, this isn't that bad. So let's convert the base. Give me a number, decently big one to keep you entertained.
64.
I love the Nintendo 64, but that's not big enough.
1008.
1008, sure. Now give me a base.
Base 12.
12, sure.
Base
Number 1008 to base. Give me another base.
13.
Sure. There you go. I'll do it too, obviously. But yeah, this shouldn't be too bad. 10. Oh my goodness. Everything's a disaster for me today. Well, it kind of is every day, I guess, but. I'm gonna type on my phone. Oh, you haven't done it. Yeah. Whatever. we did done? Everyone feeling pretty okay? What'd you get?
A to C.
Oh, that's not what I got.
Base 13.
Well, I'll write down what I have, and then we can all use our calculators and laugh at me if I'm wrong, which is great. We all love that. Okay, so I have. Oh, this is. Imagine lecturing this way from my phone. This is horrible. Oh wow. Okay, so I first. So we have the place value chart here. This. Is 1008, and so this is the ones position. This is the 12s position. This is the 144s position, and then this is the 1728s position. So 1 times 1728 plus 8 times 1 is 1736. So far, yeah? Am I doing it? No objections? Okay.
Well, if it's 108, would it be?
Okay.
Is that the conversion in base 10?
Yes, sorry, yeah, this is in base 10. So we go to base 10 first, and now we need to go to base 13. So we always start with a ones position, and then we have our 13s position, and then we have our 169s position, I think.
Yeah. And then 2197.
2197, yeah. So now, and this is where I might have messed it up. So we have to ask ourselves, 1736, how many copies of 169 fit into it? 10. Right? Because this is 1,690. So that would be 46 left over. So this is an A, and then 46 minus 3 copies of 13 is 7. And then 7 minus 7 copies of 1. Is that what I even said? It is. Okay. So then 1008 in base 12 is A37 in base 13. Good example, because it had an A in it. We managed to, unless there's disagreement. Did I screw it up? Okay. I see a bunch of people saying no, and then I see some nods, which I'm going to take to mean no, you didn't screw it up, but also it could just mean you did screw it up and I'm laughing at you, which is totally fine. I'm okay with that. But anyway, it's something that takes a bit of practice, but once you get used to it, just going through the motions, they all end up being the same problem, right? There's no real difference between any of them once you get some practice. And that's kind of true about this whole unit, because the next thing I want to talk about, and the reason why this is interesting is purely from an algorithmic perspective, is we have these other bases and we can communicate in them. So a natural question is, can we do operations in them? Can we add and subtract and multiply and divide and all that stuff in these other bases? Well, the answer is obviously yes, because computers operate in base 2. So if the answer were no, then how does your computer add? So, of course, we know the answer is yes, but we could still explore it. Again, from a mathematical lens, there's nothing special about base 2, 10, or 16. We can just talk about everything. I guess there's also base 8 octal, but there's all kinds of bases, right? And they all have varying degrees of application. So let's just explore them for fun. And whenever I say that, let's do this for fun, I'm not being sarcastic. I do think it's fun. I like math. Okay, so a natural question is adding in base 10, right? So we're going to start with adding. And all of these, when we're talking about the operation, we're going to start with a base 10 motivation, and then we're going to deconstruct that and then figure out how it works in other bases. And that's the other sort of lesson here is a lot of the things in math. So when students ask, what am I going to use math for? The difficulty is the answer is nothing but everything. Because what are you going to specifically use base conversion and adding and subtracting and other bases for? Probably not much. So what are you getting from this? Abstraction, which is exceptionally important in programming just across the board, is taking a problem and understanding how to abstract it and then put it into a program, right? So, we started with the motivation of $512 and then said, okay, well, let's take that and abstract it into a concept that we can then repurpose into arbitrary bases, right? 10 isn't special. Same thing here. Yeah, we can add in base 10, but is there anything special there? Like, is there some sort of underlying algorithm or process that we can then abstract and then, transform? So that's really what is coming out of this. So let's start with an example in base 10. And it's going to feel like we're in grade 3, and I'm sorry for that, but it is what it is. So we've got two numbers that we're adding, right? So we're doing 28 plus 45. And now we don't really need to think about this too much. Probably we write down a 3, carry a 1, and then 1 plus 2 is 3 plus 4 is 7, right? So 73, right? This is like, maybe you're not that quick with doing long multiplication, addition, and something like that. And honestly, maybe I'm dating myself. Do you even cover that in, who here is at like 18? Did you cover this in elementary school anymore?
Cover like long division
and long addition and subtraction and multiplication?
Did long addition, never did long division.
Okay, so we're not doing division here, don't worry, because division in other bases is complicated. But point is, this is like familiar, right? Like this is something that we do in grade school. But what's really going on here? So let's think about base 10 principles, right? So we have our 10 to the 0 position and our 10 to the 1 position, right? This is our 1s and our 10s position. And essentially there is a number of like pips, right? Just there's 8 dots here, and there's 5 dots here, and over here there's 2, and here there's 4. So what really happens here is we just sort of go down the list and just combine them together, right? Just take these and dump them together and these and dump them together, right? So this is 1, 2, 3, 4, 5, 6 dots. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? But this violates our base 10 principles, right? Because what that says is as soon as you have $10 in this place value, you exchange it for 1 more over here, right? So we just move that over, and so now we've got 7 dots here and 3 dots there, right? And that's really what's happening with addition, right? When we think about this carrying the 1, that's what we mean, right? We're taking 10 here. We actually got 13 here when we added 8 plus 5, but we can't write down 13. We have to carry it to the next position, right? So that's really what's happening with base 10. I hate this whiteboard now. So how can we abstract this concept? Well, we essentially borrow this, right? Because what really matters here is, we adding is just dumping everything together, right? That doesn't change no matter what base we're in. What changes is this exchange rate, right? Here we exchange 10 for 1. 10 is our base. So if we change the base, we just exchange our base for 1, right? And that's the only difference. So for other bases, the difference is the exchange rate. Right, so here we exchange at base 10, so let's look at base 5. I need more colors. So let's do the following base 5 addition. So 3, 4. Like that. So 3, 4 added to 4, 3, 4. So we still do this addition normally, right? 4 plus 4. Well, that's 8, right? So 4 plus 4 is 8. And I'm putting quotes around it because that's not entirely accurate, right? Because we're working in base 5, and actually we commonly indicate that everything here is base 5 by writing a subscript 5. So 4 plus 4 is 8 in terms of numbers, but we can't write down 8 because this is in base 5, and 8 is not a valid digit in base 5. Can't write 8, not a valid digit. So exchange our base and write leftover. So really, this is 4 plus 4 is 8. So that's 1 copy of 5 plus 3 left over. So we write down the leftover, and we're going to have to carry this 1, right? Same thing here. Now we're going to say, okay, what's 3 plus 3? That's 6. So that's 1 of our base with 1 left over. So we write down the leftover and carry the extra, the exchange. And so now we've got 4 plus 1, which is 5. Same thing. We're going to have to carry 1 exchange of the 5. Nothing left over. Right? And now you carry a 1 up top. 1 plus 0, just like that. So there's nothing really extra going on here, right? It's the same exact concept. It's just when do we carry? And that's a little harder to do in our... Oh my goodness. I feel like Edward marker hands. So here, 4 plus 4, 8. But we exchange 5 for 1 to the left, right? Yeah.
Since there's a carryover to the 3, shouldn't that be 4 plus 3 and then 7 and 2 left over?
It sure is. You are right. So this is 1 plus 3 plus 3, so that's 7. So this changes to a 2. Thank you. So that's the idea, right? 4 plus 4, we're in base 5, so that means we're above the base, which is 5, so we need to exchange 5 of those for 1 to the left. That's what the carry is. And what are we left over after exchanging 5? Well, we take 5 away from 8, we got 3, we write 3 down, right? 1 plus 3 after carrying, so that's 7. That's bigger than 5. Take 5 away, bring it to the left. What do we got left? 2. Write down a 2. Same thing here. This is 5. That's 5 or bigger, so we take away 5 to put it to the left and write down the leftover, which is 0. Right? And that's basically the addition algorithm in a nutshell. So we would say 3, 4 in base 5, 4, 3, 4, 3, 4 is 1, 0, 2, 3. Now, a couple of notes here. One, don't forget what base you're working in. I know that sounds like a no duh moment, but it's so easy to just forget that you're working in another base. And here you do this correctly, but then here you just like write 7 without even thinking about it because that's just what you're so used to, right? So be careful with that. Make sure that you're writing in the same base. And for the purposes of algorithms, if I say do the base 5 addition, I mean this, right? Go through the motions. That does not mean, so this happens every time too. That does not mean convert to base 10, do base 10 addition with your calculator, and then convert back to base 5. Because that's not doing, I would at least give most of the marks if you did the base 10 long addition algorithm. But no, everyone who does that, they immediately convert to base 5 and then just write down the answer. And I'm like, but that's not what I asked. I asked to do the long addition algorithm. So that's just a warning that it's not cheeky to convert it. However, that means it is still useful to convert to check your answer, right? So you should be able to convert all of this to base 10 and still get the same answer. So like, convert to base 10, add it up. What do you get? And then convert this to base 10. They should be the same, right? So you can use converting to base 10 to check your answers. And at that point, though, just Wolfram Alpha, it can also help you check your answers, right? So you could say 3-4 plus 4-3-4 in base 5 and Wolfram Alpha, and it'll tell you the answer. So that's the other reason why I'm like, hey, you have to do the long addition algorithm because like you could just go copy it. Which also means show your carries and whatnot. That's important to just indicate that you understand the algorithm. And you might be saying, okay, Travis, but I'm never going to do long addition. Why do I care about that? Because you're in programming and learning algorithms is interesting. That's your life. If you don't like learning algorithms, I'm sorry. That's what you're going to be doing. Is learning algorithms and ways to do things efficiently or inefficiently if that's what you have to do. So just learning algorithms ends up being fun after enough time. So that's the other reason why I presented. It's just another algorithm, and I will probably, knowing that information, because yeah, I'm not surprised I don't cover long division anymore. That means if I include it in an assignment, I will explain to you the algorithm for long division. If you're computer programmers, it's not hard to understand, but if you've never been presented it, you'll have to actually learn it. But anyway, I think that's all for now. We got 5 minutes left, but I don't think I have enough time to get into it. We'll talk about subtraction and multiplication next class, and then it'll just be a quiz, shockers on what it's going to be. And then I think according to the schedule, I am giving you like a week to work on the group project. I'll have to check. So I think there's basically no lectures the week after, which in retrospect, I should have done that this week. So then you would have had 2 weeks where people just didn't show up. But well, I'll check the schedule.